Hi folks, Mr. Kozer here. I want to help you to learn today a little bit more about an idea called standing waves. So I'm going to draw a few pictures and then support what you're working on with the sheet for today. So here's the idea. We know that we're after this topic called standing waves, and I want to set up two starter ideas to get you going, and that is thinking about what happens when waves meet. So let's imagine we have a string or a spring like you've seen us use, and we have a wave coming in from each end, one coming from the left and one coming to the right. As you saw in some videos earlier, when those two waves meet, they make an extra tall wave. And then of course after that they keep going. But this is called constructive interference. That is, when the waves meet, they make a really tall wave. And I want to point this out because this is what is causing what we're going to know as an antinode in standing waves. I'll show you that in just a minute. Let's think about another situation where you might have a wave up on the top coming in from one way, but a wave down on the bottom coming in from the other way. Now, when those two waves meet, strangely, they can cancel each other out right smack to zero. And we often refer to that as destructive interference. That is, they cancel each other out or they destruct each other. And the point is, that's what causes this thing we refer to as a node. So what you've seen and what you're going to continue to see is situations where we think of maybe a string with waves in it, and we set up what's called a standing wave, where the material goes up on one side, down on the other side, and it does something like this. And then over time it vibrates back and forth, so you might see it switch to the opposite position, and it'll sit there and flip-flop back and forth. And of course it looks like it's standing still, hence the name standing waves. But really what's going on is there are antinodes created by the waves meeting in such a way that they always interfere constructively. And in this case, there's two antinodes, these two bump areas. And there's nodes at the places where the waves always cancel each other out. And in this case, it happens that there's three of those, and you can see the places on the two ends and in the middle. So these are called standing waves. And that's a little background that'll get you started. Now, we also know when we think about waves that one wavelength has to include both a crest and a trough. So this term is not real new by now, but it's called wavelength. And it just means exactly that, the length of one wave. We use the Greek letter lambda, L-A-M-B-D-A, lambda, to represent wavelength. And again, the point is that anytime we have, just like in harmonic motion, a complete cycle with the medium moving to one side and back to the middle and to the other side and back, we call that one wavelength. So these two ideas are going to set you up for what we're going to look at today. So this is a worksheet to work on today about standing waves, and I'd encourage you to read this top section. It talks about the idea that a wave confined to space is a standing wave. And that's what we have here in this picture. And again, a standing wave, it looks like the waves are standing still, while really they're interfering all at once. So you'll notice that standing waves also have harmonics. That is, we can have different numbers of nodes and antinodes show up. And this picture you've seen before in the slides, and these numbers up here are referred to the harmonic number. But really all we're doing is we're just counting up 1, 2, 3, 4, 5. How many of those bumps that there are in each wave pattern? Or the better name for the bumps, of course, is antinodes. So we're counting up how many antinodes, and that tells us what harmonic that we're dealing with. So today's job is to take a look at this sheet. First, read the top, and then the first job is to identify these pictures. So take a look at the pictures and decide, well, which harmonic is represented by each of these. Now, here's a hint. Again, it just simply is the number of antinodes. So you can pretty quickly see we have 1, 2, 3, and 4 antinodes represented in these 4 pictures. So you just have to decide which ones are which. That's the first job. Secondly, I'd like you to take the letter A and label the antinodes, and you can do something like this with a line maybe, like in this case there's 4 antinodes. And then I'd like you to also label the nodes like it says in the directions, and again you can do that with lines. So you want to label where the nodes and the antinodes are in each of these patterns. And again, the goal is we're just getting you comfortable with what those mean. So that's the first section, is to get really comfortable with standing waves. Now, in the second section, I want you to start to think a little bit about how many waves are contained in each picture. If we back up a minute and we take a look at our picture over here, you'll recognize again that one wavelength has both a crest and a trough, or an up and a down, or another way to think of it is two antinodes. Two bumps are required to make one wave. So if we look at each of these pictures, the question here is how many waves are represented in each picture. Let's look at picture B. That's a little bit of a tricky one. You notice picture B has 3 antinodes. So picture B, it has 3 antinodes, but we know that one wave or one wavelength has 2 antinodes. So if we look in this particular picture, we know that one wavelength has 2 antinodes. So one wavelength would start here and go over to here. So in this case, we'd have half, 1 and 1/2 waves, 1.5 total waves in picture B. So picture B, how many waves is it? It's 1.5. Of course, if you look back to picture A, that one's a little easier, right? Because there's 2 antinodes. So picture A is just 1 wave, and so forth. I'll ask you to try to figure out the other 2. Now, the length of the string, of course, that just comes right from the picture, right? Write the total length of each string in the next column. So we just look at the pictures and we can tell that. So for example, picture B, the total length says 15 meters. So for picture B, I'm going to write 15 meters here. Now, how can we find the wavelength? Well, if we know, as it says, you can figure out the length of one wave in each string. If we know the length of the string being 15 meters is equal to 1 1/2 waves, well, I think we can figure out how many waves there are, yeah? So let me write that over here. If 1.5 wavelengths equals 15 meters, well, if we want to get lambda by itself, we just have to divide both sides by 1.5. That is, lambda would be 15 divided by 1.5. Gosh, that sounds like 10. It's 10 meters. So the wavelength is 10 meters. Now, you might also just be able to look at it and say, if this whole thing is 15, well, each one of these pieces must be 5, so it's 5, 5, and 5. And if I want to know how long it is just for 2 antinodes, yeah, that's 2/3 of that material, or that's 10 meters. So you can also look at it and think about it. But a good math way to do it would be like this. So again, your job today is to practice and work through the rest of these. And then finally, a little more practice. Here's 2 students wanting to use a rope that's 12 meters long to make standing waves. Now, 12 meters, that's a long rope, right? So the conversation here is about you getting comfortable with that and then practicing by drawing the harmonics. So the harmonics here are just the same as we saw on the chart on the first page, and you just want to sketch these in. So for example, on the first harmonic, all you're going to do is have one antinode all the way from one end to the other, something like this, and I'll draw a dotted line on the bottom half. But for the sixth one, boy, we've got to have 6, right? So we've got to have 1, 2, 3, 4, 5, 6. So by the time that we're done, we have 6 antinodes. Again, my drawing isn't perfect. Yours doesn't have to be either, but we want to show 6 different bumps in that, and so forth, working your way through those. And then finally, I want you to practice. So harmonic 6 that we just did, bump, 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 that has 6 antinodes. But notice we can also think about how many waves that is. So if each wave is 2 antinodes, well, there's one, there's another, and there's another, yeah? So here's a wave, and here's a wave, and here's a wave. Hey, 6 antinodes, that's 3 waves, yeah? And just like before, what's the wavelength? Well, if we know it's 3 waves is 12 meters, Well, then one wave just means divide 12 by 3. So 12 over 3. That sounds a lot like 4 meters. Okay, so we're thinking about getting comfortable with how many waves there are. One more reminder, a wave is made up of 2 antinodes. So we have to look at the picture and ask yourself, how many antinodes does it take to make a whole wave? 2. And then how much length is that? Finally, harmonics, they're useful all over the place. And sometimes they're dangerous. It really depends on the circumstance. Sometimes harmonics are used in sound. I can use harmonics to tune a guitar, for example. But sometimes they're good, sometimes they're bad. So I simply want you to hop on the interweb today and take a moment and search the word harmonic and see what you can find, and find some interesting thing and write a little bit about it here. Just give us a little bit of feedback. All right, so once again, our goal here is to recognize what is a standing wave and to recognize that a wavelength is 2 antinodes and to have some practice with that. All right, work through that set of problems, please, and I hope you have great progress.